I need to acknowledge that my co-authors here who did all the work. I'm just a figurehead. Amy Fagan, Katie O'Sullivan and Patrick Donahue have slaved away many hours creating the crystal-sized distributions that they alluded to in the lightning round. But what this has produced when you bring all these different hard-fought data sets together is a method that I think is going to be intriguing for being able to distinguish between these very igneous-looking impact melts that look like pristine basalts or basalts, and from each other. So that, for example, if we do go to South Pole Aitken, sorry, let me rephrase that. When we go to South Pole Aitken, we will know what is impact melt and what is not, and we won't do it in the traditional way, because when the first Apollo samples came back, there was a lot of confusion with regards to, well, impact melt, pristine basalt. Sample 14310, now the classic example of an igneous looking impact melt, was originally documented as a high alumina Mare basalt from Apollo 14, and a number of papers in the early 70s actually quoted that. This was debunked through experimental work. Another way to do it is to destroy a lot of the sample to do highly siderophile element analyses to show that they're either higher in terms of they incorporated a meteoritic component, or lower, they were actually derived from the lunar mantle. Again, but this assumes then that you've actually incorporated a bit of the meteorite into the impact melt. So there are examples of low siderophile element abundances in impact melts. So again, these distinctions become time consuming, and this one is also a little time consuming, but once the database is built up, it's a lot quicker than actually trying to do a highly siderophile element analysis or run the different experiments. So the work presented here presents or shows the promise of quantitative petrography in distinguishing between these pristine melts and impact melts. And we're going to focus upon the minerals, plagioclase and olivine. So here we have a bunch of photomicrographs, and can someone tell me which ones are the impact melts? It's sort of difficult when you look at it just down the microscope to say which one is which. Well, let me put some sample numbers up there. The ones in the light blue represent pristine Mare basalts, the ones in yellow represent impact melts, and 12038 is the only example of a feldspathic basalt from Apollo 12. It's considered to be pristine. However, I'm going to present evidence to suggest that it could be an impact melt, which may be heresy in some places, but, well, whatever. We'll deal with that as it happens. So what do we mean by crystal size distributions? What we're actually doing is quantifying the sizes and distributions of different mineral species within a given thin section. And it is then plotted up in terms of a corrected length, because we're taking a 2D slice and then trying to convert it to a 3D image. One thing that is showing promises is micro CT scanners to actually take a whole rock sample and do this in 3 dimensions rather than trying to convert 2 to 3 dimensions from a thin section. And then we're plotting the natural log of the population density. What we see up the top here is this nucleation density is where we see the intercept, and the slope is related to the growth rate and the residence time of the crystal in the magma. And you can see here there's a number of ways to deviate from a linear relationship in this negative correlation. So smaller crystals have higher populations, so on and so forth. What normally happens is you see this downturn at the upper end in the smallest populations, because we reach the resolution of the image and we cannot count accurately these. So you'll see a lot of the actual crystal size distributions having this downturn. So what we're also looking at, not just the impact melts, but also a number of Apollo Mare basalts. We know these are Mare basalts. And again here, this is where Katie and Pat have really come into their own with regards to working on the Apollo 12 and the Apollo 17 Mare basalts and doing these crystal size distributions. And I just want to point out, this is a beautiful thin section of 12021, 139. I mean, look at that. That's just absolutely spectacular. and I will stop raving about the thin section. We also look at, and this is part of Amy Fagan's work, looked at the Apollo 14 olivine vitrifiers, traditionally very high MgO content. They have dark quenched glass, but a lot of these little olivine crystals with them. They're also creep rich, and you look at the traditional rare earth element. This is not a log plot, this is a linear plot, so you can see these beautiful rare earth element patterns, light rare earth element enriched. This big europium anomaly, and no, this is not one of Amy's plagioclases. This is actually a whole rock composition from these different olivine vitrifiers. And if you're very lucky, you actually end up with a remnant olivine in your thin section, such as we have here in this particular example. However, these are some other photomicrographs, and up the top there, what you're seeing are these pristine Apollo 12 olivine vitrifiers. Well, how do we know they're pristine? Well, again, we use the traditional methods of highly siderophile element abundances, and then I'll show that, confirm through the crystal size distributions, that they appear pristine. And here we have the impact melt. So you can see these are quite similar in their textures when you take a first look at them. It's the doing the quantitative petrography on the olivines within these that is really starting to pull these apart, and just show from a thin section we can now actually see the distinctions between the two. So let's look at the data. We have Apollo 14 impact melts in the solid black line, Apollo 16 impact melts, more work from Amy Fagan here, and you can see how they're coming out. They look distinct from each other. And then in the grey we have the Apollo 14 Mare basalts, and in a different talk, the Apollo 14 Mare basalts, their crystal size distributions appear to correlate with their composition, which is really quite bizarre. But it's that's the way the data have fallen out, but don't have time to get into this. So let's look at the olivine crystal size distributions. Again, more work from Amy, and here the dark blue represent the impact melts, and these represent the pristine Mare basalt. So you can start to see immediately that we've got a distinction. But if you look at the scales here on these two, especially the corrected length scales, you see a variety of different crystal lengths, and we started to compare apples and oranges. So what we're trying to develop here is a method to sort of normalize this, and what we've done for plagioclase, this is the method that we've come up with. Samples will exhibit this variety of different crystal size distributions. So we've taken the steepest slopes between 0.1 and 1 millimeter. These populations are present in all the samples that we've looked at. The interesting thing, you see this downturn. So what we've done here, we've just said we're going to take the crystal size distribution length within this range that shows the continuous slope. As soon as it starts to downturn, we don't use those data bins. So we're just taking this sort of linear slope here, and then we're back calculating, well, where does it intersect the y-axis up here to calculate the nucleation density. For the olivine, we're using a similar approach, but because the olivines are smaller, we're looking at less than 0.35 millimeters, and again, using that same rationale that I just described for the plagioclase. Well, what does this mean when we look at the data? Well, here we've got this CSD slope plotted against the intercept, or the nucleation density for that particular size range. So here we got the light blue being the Apollo 14, the blue circles being Apollo 12, and then the yellow squares being Apollo 17. And this is just for plagioclase. And there we see the impact melts starting to fall out over here, now very close to the Apollo 14, but here's 12038. This originally, people thought that this was in fact the pristine Mare basalt. We're starting to question that on the basis of our textural analysis, and going back through the literature, and maybe we're starting to perform some of the old analyses, or redo some of the analyses to look at the actual composition of that. If we put regressions in, we can see pretty good regressions with these different data sets, suggesting that the nucleation and the crystallization of the different samples are pretty similar. It does show a distinction with Apollo 14, and the impact melts appear, at least for plagioclase, appear to fall out over to the right of the diagram. Olivine is a little clearer. What you see here, we've done the same thing, the same sort of plot. Here are the impact melts, here are the pristine Mare basalts. Now what you'll see in this particular diagram is that our population is much lower. This is ongoing work, but we believe that this type of analysis just from a thin section will allow us then to be able to clearly distinguish between impact melt and pristine Mare basalt. So in summary then, plagioclase CSD slopes appear to be more gentle in impact melts than pristine basalts, suggesting that they crystallized over a longer period in those impact melts that we've sampled, both from 14 and 17, and a greater proportion of larger crystals are in the melts relative to the Mare basalts. For olivine, it's the reverse case, which is quite bizarre, but it gives you an idea of the crystallization environment in which these crystals grew. So, for example, for plagioclase, suggest we got fewer crystallization nuclei for plagioclase in impact melts and more for olivine relative to the pristine Mare basalt. So this is going to be implications for future experimental work. And if you go back to Gary Lofgren's pioneering work in the 70s, it actually suggests it's the opposite of what his conclusions were, which was a bit of a shame. But again, this is something Gary and I are going to be talking about to actually come to some resolution on this. And maybe I've not read his paper properly, which is probably the case. Focusing on the small crystal populations for plagioclase and olivine allows the impact melts to be distinguished from pristine Mare basalts. What are the implications for 12038? That's better. I'll keep you in my peripheral vision now. What are the implications for moonrise when it actually does go to SPA? I think these are quite huge because it means preservation of a valuable sample. You're going to have to make a thin section of them, but from that we don't have to do destructive analyses to see which ones are the impact melts. And again, this is something else that we can apply to our crystal stratigraphy work because it allows us to get into many more details of how impact melts actually crystallize and how they evolve. And I just had to put that up. Thank you very much.
Does anyone have anything they want to say to Clive? Anything?
Clive, I think you're overselling this a little bit because you're saying that this is the only non-destructive way that you can make such a determination. But I think you're overselling this because there's another non-destructive way. You made a thin section, that's not destructive.
One can measure the metal compositions, and people have been doing that for a long time. And for example, in 12038, the metals in 12038 corroborate the evidence from the bulk destructive RNA measurement of the highly siderophile elements. They show extremely low nickel content in the metals in 12038. So you just have to have a thin section, and you have to stumble upon a metal grain, and you can non-destructively, if that's non-destructive, you can make that an evaluation of the degree to which siderophile elements have gotten into the mix. And if I may go on.
I don't know, may you?
If I may go on, it's true that you can cite cases from the Earth. There are lots of them where impact melts don't appear to be contaminated with siderophile elements. But it's a different kettle of fish because the moon has a megaregolith at the surface, which has about 2% contamination equivalent, at least, of highly siderophile elements. So it's much harder to manage to avoid contamination of siderophile elements when you produce impact melts on the moon.
Okay, point well taken, Paul. We need to look at the metals. That's for sure. So, Carl.
Carl Allen, JSC, elegant work, and hats off to students who actually do this sort of thing.
Well, they actually get paid to do it. I don't think they do it out of love. But
Oh, okay. we may have to try that. You had mentioned X-ray CT scanning for these small crystals. Can you actually cross-correlate and do that well enough to make these determinations?
Well, I've just discovered that we have a micro CT scanner on campus. I have not had the time to actually go test it, thin section versus the micro CT, the three-dimensional reconstruction. That's something that I'm hoping to get to this summer. But I will keep everybody posted with that, probably at